Hello Year 12 single mathematicians. Just going to go back to 1.1 in the Year 2 pure maths textbook. Something I tried to avoid teaching up to this point, but I think it's a good time to actually go back and do it right now. It's a form of proof, and if you remember, mathematical proof was one of the harder things that we studied in the Year 1 textbook. And this is a new type of proof called proof by contradiction. I'm going to give you a quick warning at the start of this video that I've got a feeling this video is going to be pretty lengthy. I'm going to cover quite a bit and do a lot of examples which are complicated. But I just encourage you to just re-watch the video, try and follow the logic as best as you can, and ask as many questions in the live lesson, if you have any, to try and get your head around this. And that's pretty much it. So the first thing I'm going to do, which is I'm going to refer to this a couple of times in this video, is what the word contradiction means in the mathematical context. So it's basically what it would mean anyway, and it's just a disagreement between two statements, which means that both cannot be true. So it's just working under the assumption that if you've got two statements that disagree with each other, then they can't both be true. Now, move on to a few mathematical and some non-mathematical statements. And I'm going to introduce this idea of what's called the negation of a statement. And the word negation of a statement tends to get confused with the opposite of a statement, which I don't really like to use that word. The only other word I would use, which you might be able to get your head around, is the complement of a statement rather than the opposite of a statement. So, let's reveal some of these statements. So you have, what's that, six statements? Yes, 6 statements. Now, let's look at them one by one. So, let's pick on the ones which are without a mathematical context. So, all sheep are white is the statement. Now, I'm looking for the negation of that statement, which is the complement of that statement. So that would be something summarising everything apart from all sheep are white. So you can't just say all sheep are not white. That wouldn't be good enough in this case. So the true negation of this statement would be there is at least one sheep that is not white. Because they're making a very bold claim that all sheep are white, and your negation would be there's at least one sheep which is not white. Let's go for the other statement, which is non-mathematical, which is all flags, so flags of different countries, are rectangular. So the negation of that would be quite similar again. There is at least one flag which is not rectangular, which I think is actually true. I think the Nepalese flag isn't rectangular. But that would be the negation of the statement. It's just not all flags are rectangular, all flags are not rectangular. That's not the negation, that's the wrong idea. It is everything apart from that statement. So all of the possibilities apart from all flags are rectangular in this case. Right, let's try the mathematical ones now. The first one says there is no greatest even integer. There is no greatest even integer. In other words, like there's an infinite amount of even integers. So the complement or negation of this would be there is a greatest even integer. That would be the negation for that one. This one's a little bit more complicated, so I'm going to come back to that at the end, but I'm going to skip on to pi is an irrational number. Irrational is something which can be which cannot be expressed as a fraction. Irrational cannot be expressed as a fraction, so the negation of this would be pi can be expressed as a fraction, or in other words, pi is rational. Okay, last statement. There are no prime numbers that are even. So they're claiming there are no 0 prime numbers which are even. And the negation of that would be there is at least one prime number which is even. Let's go back to this last one. If n squared is odd, I should say then n must be odd. So they're claiming if n squared is odd, then n must be odd. Now the negation of this is quite difficult to write. And it would be something like this. So there is at least one value of n such that n squared is odd, but n is even. So they're claiming, because they're claiming if n squared is odd, then n always has to be odd. And the negation of that is at least one value of n such that n squared is odd, but n is even. Now, you got statements on the left, negations of statements on the right. In maths, only one of these can be true. Either the statement is true or the negation of the statement is true. Like if we quickly went through these, the first statement is there is no greatest even integer. We agree with that statement. That would be true. The other one would be false. The second one is if n squared is odd, then n must be odd. The more you think about that, you'll realize, yeah, that is a true statement. This other statement is false. Pi is irrational. Pi is rational. Pi is irrational. It can't be expressed as a fraction. All sheep are white. There is at least one sheep that is not white. The negation is correct in this case. All flags are rectangular. There is at least one flag which is not rectangular. Well, I think the Nepalese flag is non-rectangular, so the negation would be correct in this. But there's no mathematical universe where both the statement and the negation of the statement can be true, because this is going to be key for our proofs later on. There are no prime numbers that are even. There is at least one prime number which is even. Yeah, 2 is a prime number which is even, so the second statement is correct and the first one is false. Now if you want to briefly practice negations of statements, then you can skip to the exercise now and pause the video, and it's page 4, exercise 1A. And to practice the negations of statements, you might want to do questions 1 and 2. If you're not quite getting this, you might want to try 1 and 2 first before I go into some really complicated stuff. So pause the video if you need to go through some negations, questions 1 or 2. Right, let's go into the concept of the actual proof itself right now. So a normal proof, which we were doing in the year 1 book, would be you start with statement that you need to prove. you would follow logical mathematical steps. Or maybe there's something in between that I might want to write in. So you normally start with an obvious fact, something you assume to be true without much debate. Then you follow some logical mathematical steps, and then you end up with a statement. So you started off with something true, something obvious. You followed logical mathematical steps. You didn't break maths, so everything stayed true. And then you ended up with a statement, which meant the statement must be true itself. And that was a version of proof which you'd finish with a proof symbol. Now, proof by contradiction is completely different. It kind of uses the fact that we did above, which is if you've got a statement and the negation of the statement, only one of them can be true at once. So if I knew one of them was false, I automatically know the other one is true. Like if I am told, if you look above, pick on any pair of these, pick on the flags being rectangular one. If I know one of those is false, that must mean the other one is true. Okay? And let's see how this logic will work, because what happens with this is you don't actually start off with a statement. You start off with the negation of the statement, okay? So you start with the negation of the statement. And you follow logical mathematical steps. And because the negation is false, even though you haven't proved it, what will happen is you'll end with a false statement, something which is mathematically impossible. Okay? And if you start with a negation which you are hoping, kind of working under the assumption that's true when it's not, and you follow logical mathematical steps which would keep it true, but then you end up something which is completely false. This is back to my first sentence at the top, which is a disagreement between two statements is called a contradiction, which means that both cannot be true. You can't go from something which is true in the sense of I'm kind of assuming it's true and end in something which is false by using normal logical mathematical steps. And what that means is you arrive at a contradiction. The symbol for a contradiction is this symbol, because you've got two statements which are opposing each other, one which is true, one which is false, which means that negation is false. And if the negation is false, the original statement must be true. It's kind of the logic, okay? So original statement is true. End of proof. So you kind of end up proving that the negation is false. And by doing that, the original statement is true. That is how I could best summarize proof by contradiction. Proving that something is false, therefore, like the direct product, the result of that means the other statement would have to be true. Right, let's see what this looks like in action. Sorry this video is going to be so long. So let's prove there is no greatest odd integer by contradiction. Right, so they're making a pretty big claim. No greatest odd integer. And the first thing I've got to do is write down the negation of the statement, and I assume is true. Assume the negation is, which would be no greatest odd integer, means there is a greatest odd integer. So assume there is. Okay. And remember, I'm trying to show that this is false. Okay, I'm assuming it's true, but I'm going to use logical mathematical steps until I get something which is obviously false, which is called a contradiction. So I kind of want to find an integer which is bigger, an odd integer which is bigger than this. So I'm going to call n the greatest odd integer, and find a number which is bigger than that, which is odd. And the easiest way to do it is to consider n plus 2, which is an odd number plus an even number, which produces an odd number. And now we've just got n plus 2 is odd, and n plus 2 is bigger than n. But we were working on the statement that n was the greatest odd integer. So this is the contradiction. This is the thing we were looking at, something which is mathematically false based on what we assumed. So that is a contradiction. Don't have to write the word contradiction. You can use that symbol. And then you can say, well, therefore, that original statement is true. There is no greatest odd integer. We've effectively just verified that the statement was false, or the negation of the statement which is false. So that's just a form of proof now you can use. SCG number 2. Okay, prove by contradiction that if n squared is even, then n must be even. So firstly, the negation for this is really difficult to come up with. It's very similar to the ones we did at the start. So they're saying n must be even. So all values of n must be even. Now the negation would be there is at least one value of n which is not even. So we're going to assume that's true. So assume there is at least one value of n such that n squared is even and n is odd. Okay, in other words, n is equal to 2 times something plus 1. That means n is odd. That is the definition of an odd number. Now, I'm going to follow logical mathematical steps and come up with something which is obviously false. So they talk about n squared. So let's see what n squared would be for an odd number. If you expand in this bracket, you get 4k squared plus 4k plus 1. Remember, you want a contradiction. You need to show this is false. They are claiming n squared is even, or we are claiming n squared is even. If I took out a factor of 2, that is not an even number. That is equal to an odd number, which is the contradiction that you are looking for. You started off assuming some false statement was true, you followed logical mathematical steps, and by no surprise you ended up with something which is false, and that is what you wanted to achieve. And by doing that, you can say therefore, I'm not going to write the entire statement out again. I'm going to cheat and just write the original statement is true. End of proof. Okay. So yeah, there's some key things in this proof by contradiction. It is this first step, which is assuming the negation is true, then trying to follow some steps and forcing something which is false to happen at some point. So yeah, and then finish off with the conclusion. So it's like a 3-part kind of thing: assumption, logical steps to a contradiction, and then a conclusion at the end. Right, the next two proofs, or the next two examples, are ones which are very difficult to come up with these by yourself. But they are ones which just is guaranteed that one of these is going to come up in the actual exam, so you may as well just memorize them if you don't fully understand them. But yes, proof that some surd is irrational. I'm going for root 2, but it could be any surd. Right, if root 2 is irrational, then the assumption, the negation of this, is root 2 is not irrational or root 2 is rational. Now, that's obviously false, but when this is part of this proof, we work with false statements and prove they're false. Right, if root 2 is irrational, then it can be written as a fraction. Okay? The one, obviously fractions themselves can be simplified, so I want this to be the simplest fraction. So I want a and b to have no common factors. It's quite a key thing in this proof, actually. The thing that you wouldn't necessarily write down if you hadn't seen it before. So let's say a and b have no common factors apart from 1. In other words, highest common factor is equal to 1. That's all what that means. Right. Follow logical mathematical steps. Some logical mathematical steps would tell you that you don't like square roots, so you would square both sides. Some logical mathematical steps would tell you to get rid of fractions by timesing by the denominator. Okay. Now this is a key bit of the proof. That left-hand side is a multiple of 2. Which means the right-hand side is a multiple of 2. Okay. I've just proven this is done in EG number 2 as well. N squared is even, then n must be even. A squared is even, a must be even. You can safely say that a is also a multiple of 2. If a squared is a multiple of 2, which I've just kind of rearranged to find, then a would have to be a multiple of 2 as well. If a is a multiple of 2, I can write it as 2 times something. Right, a logical thing to do next would be substitute that into the original equation. So we would have 2b squared equals 2c squared. A logical thing to do would be to expand and simplify. And divide by any common factors. B squared equals 2c squared. Okay. This is a multiple of 2. This implies b squared is a multiple of 2. which in turn implies B is a multiple of 2. Now, it doesn't look like I've done much right so far, but believe it or not, the proof is done. That is it. There's enough information on this page for you to conclude that this is a contradiction. I've written enough on the page which proves this to be false, and it stems from a combination of that statement there, A, B have no common factors, and the fact I've just shown that A is a multiple of 2 and B is a multiple of 2. That is the contradiction. They can't be multiples of 2 and have no common factor. So, contradiction. And then you can finish off the proof by saying, therefore, root 2 is irrational. Okay. And that would be how to prove a surd is irrational. Exactly the same proof for every single one, effectively. The last type of proof you need to know for this very long video is prove by contradiction that there are infinitely many primes. So this is another one which is very difficult to come up with this by yourself. So it's one that a lot of you will have to just memorize. But the structure is exactly the same. Assume the negation. If they're claiming there's an infinite amount of something, the negation of that would be there's a finite amount. Now, if there was a finite number of primes, I could list them and eventually the list would stop. So if I started listing them prime 1, prime 2, prime 3, all the way up to this finite, the list will stop at prime, I'll call it n. Now this is the tricky part. Obviously there's infinite many primes, so we need to somehow come up with a contradiction. So I've got to try and come up with a new prime which is not in this list. And the way to do it is considering the following, which is the product of all of the primes plus 1. Okay, if you took the number which was the product of all of the primes that you think are in this list, or think that exist, and you add 1 to it, then if you go 1 by 1, and divide this prime, this n by each prime number individually, there'll always be a remainder of 1. So n divided by p1 gives remainder 1, because p1 goes into this number, but 1's left over. N divided by p2 gives remainder 1. And if you did this for every single prime in the list, you're always going to get a remainder of 1. In other words, none of the primes go into n. Now, if that's true, then n itself, by definition, would have to be prime. Because if I had a number and no primes go into it, that number itself would have to be prime. That is a mathematical fact about prime numbers. So that says, therefore, n is prime. But not on our list. Which is the contradiction. How can you list out primes a finite number and then come up with a prime which was not on that list? That's the contradiction. So then you can say, therefore, there's infinite many primes. End of proof. Now hopefully that's the best I can do actually on explanation of proof by contradiction. It is kind of counterintuitive when you first try it, because you end up working with statements which are obviously false. But the idea is working with a statement which is false should lead you to statements which are even more obviously false. And if you can do that, that's called a contradiction. And then you end up proving the original statement indirectly, effectively. And that's pretty much it. And the questions I would like you to do is everything from exercise 1A. So exercise 1A on page 4, and it goes on to page 5 as well. And that's pretty much it.